Okay, everybody, so I would like to review a couple basic facts about series that are useful for understanding what we're doing right now in class. And I would like to highlight basically two facts. So the first, so number one is the idea of a geometric series. So geometric series. Okay, and this is essentially the following thing. Imagine that I consider the following sum. So 1 plus r squared plus r cubed plus ... all the way to infinity. So I could call that sum, I could give it a name, so why don't we just call it, let's call it S. So that's the sum, and so the question is, what is it? So under what circumstances does this sum converge, and if it converges, what does it converge to? So it's useful actually in this case if one to think about it if we just start with actually an example. So suppose I let r be equal to a half. So if I have a half, then this sum S is equal to 1 plus a half plus a quarter plus an eighth plus ... And a sort of pictorial way to think about this sum is the following. So as you know, I can't draw, but I will try my best. If I draw a block which has an area 1, so let's suppose that has an area 1, then what this tells me to do is take a block with area 1 and then add to it a block which has area half. So this second block has area half, and then add a block of area a quarter. That one I drew badly. Maybe that's a quarter because it's a half of a half. And then I have to do one which is a half of that, which is this, and so on and so forth. And you see basically that what happens is that I'm going to end up filling in this entire square here, and that ultimately what's going to happen is that we're going to basically fill in this entire area, which is going to be 2. So that's going to be the area. So so how can we see that that's actually... So the way to do that is the following. If I write that S is equal to 1 plus r squared plus ... then if I simply do the following algebraic manipulation, I consider the quantity r times S, so that is r plus r squared plus ... And if I then subtract the two, so I'm going to subtract the two, so I'm going to get S minus rs, so S minus rs on the left side, and on the right side, then of course what you see is that this r cancels this r squared cancels this r squared, and so on and so forth. And so the only thing that's left on the right-hand side of the equation is 1, so that gives me equals 1, and that of course implies that S is equal to 1 over 1 minus r. And if I then use that r is a half, then that implies that S is equal to 2, which is what we found pictorially on the previous slide. So, okay, so now the question that we're concerned with in class, so this geometric series, this so-called geometric series comes in many different ways, but the question that we're concerned in class is really under what conditions does a series converge. And so, for example, you could look at this S here and ask when does it converge. So it should be clear to you that if we were to, for example, put r equals 1, so let me actually write r equals 1 right here. So if I put in r equals 1, then S would be 1 plus 1 plus 1 plus 1 plus ... And that series simply doesn't converge. If you add 1 to itself infinitely many times, then you get infinity. And indeed, you should therefore be happy to see that if you look at this formula here, if you plug in r equals 1, then of course it also diverges because the denominator vanishes. 1 minus 1 is 0, and S is infinity. So in fact, if r is any number that is bigger than 1, then you can also see that it still diverges. And the reason for that is that if r is bigger than 1, then r squared is bigger than r, and r cubed is bigger than r squared. And so in that case, the numbers are actually increasing, and there's no way that that's going to converge. So for the thing to converge, one needs the numbers in this sum to decrease as you get further and further out. So for example, if we were to write the nth term here, I'll use a different color. Why not? We should enjoy colors in life. So r to the n plus r to the n plus 1. So basically we need these terms to decrease in size, and that actually happens when the magnitude of r is less than 1. So when the magnitude of r is less than 1, these numbers decrease in size, so there's some chance of the sum converging, and in fact it is indeed the case that this formula for S is actually correct, and that the geometric series is 1 minus 1 over r. Okay, so now let me an example in and of itself, but its importance goes well beyond it because of a bit of an analogy that I described in class on Monday, which is that if I consider a power series, which is of course what we're doing right now, we're considering functions which are represented by infinite sums, from n equals 0 to infinity of a n x to the n. And as I sort of indicated, I mean, when one's writing a series as an infinite sum, one's dream, of course, is not that all infinitely of the terms matter. If they do, there's no way it's going to work, but that only a few of them matter, and so the series has to converge. And the question is under what circumstances, so when does this converge? And there's a simple, sorry, this is bad handwriting, so there's a simple way to think about this, which is essentially the following. So what we do is we simply compare this series that we've written here, this power series, to the geometric series. And so I'm going to just write it out. So if I write y is equal to a0 plus a1x plus a2x squared plus a3 x cubed plus dot dot dot, and then the geometric series, what I called S, is equal to 1 plus r squared plus r cubed plus dot dot dot. And we decided on the previous in the previous slide that basically that as long as r is less than 1, that this series converges, and we even know what it converges to. And so the question is, what is the analogous the analogous criterion for this power series? And the sort of simple thing to do, which turns out to be rigorously correct, that I'm fairly certain that all of you have proven this rigorously in a math class at some point in your life. If not, we can certainly do that. But the question is really, what is the analog of r? And the analog of r, so I'm going to call this quote r, is that what you do is you take the ratio of the n plus first term, a n plus 1, x to the n plus 1, and you divide it by the nth term. So, and let's just take absolute values. So that's the analog of r, and you'd really like this when n is large. So you'd really like this to be true in the limit as n goes to infinity. Now, the reason that this is the analog of r is because, of course, if you take the ratio in this equation of the nth plus first term to the nth term, then you get exactly r, because the nth plus first term is just the nth term multiplied by r in the geometric series. And so this is the sort of analog of r. That is, as n gets bigger, then the question is, if you look at the ratio of the n plus first term to the nth term, then that's essentially giving you r. And the convergence criterion then is clear. It's that this analog of r has to be less than 1. Right, and if one then just, and this is what we wrote down last time, so if I write down a n plus 1 x to the n plus 1 over a n x to the n, absolute value of everything, then of course the x to the n cancels, so this is really just a n plus 1 over a n times the absolute value of x, and this has to be less than 1, so that implies that x has to be less than a n over a n plus 1 in absolute value, and really this is the limit as n goes to infinity. And this this formula here that we're writing down right here is the definition of what we defined in class as being the radius of convergence of a series. And this is the range of x where the series actually converges, and this argument shows that it converges because of by comparing the series to the geometric series.